AI agents sit at the intersection of deterministic code and non-deterministic large language models. Your application needs to call databases, invoke APIs, and execute business logic with predictable behavior. However, the large language models they focus on reasoning about user intent, selecting the right functions, and generate coherent responses. So these are two different worlds that need to bridge together. And this is where semantic kernel actually comes in as a middleware layer, where semantic kernel provides the kernel abstraction through plugins and function calling to the agent framework and multi-agent orchestration patterns. The core challenge it solves is that enterprise applications need more than raw LLM API calls. When you're building something real, something that's actually going to handle actual users and actual data, you do need structured orchestration. You need memory that can store and recall relevant information as well. You need to execute deterministic functions, things like, for example, database queries and API calls wrapped around the non deterministic nature of language models. Semantic Kernel is Microsoft's open source SDK designed specifically for this. It helps you build AI agents and multi agent systems that combine large language models with conventional code, with plugins, and with external data sources. It is available in C Sharp, Python, and Java, and the version 1.0 designation matters because it signals the stable APIs and a commitment to non breaking changes. The C Sharp implementation is the most mature of the three, which makes sense given the Microsoft ecosystem is in C Sharp as well. However, it does work with other languages just as normally. Now, the mental model I want you to hold is that think of semantic kernel as a middleware layer. It sits between your application logic and the language model. The kernel object is a central orchestrator. It routes requests, manages plugins, and handles function calling. Your code defines what the AI can do through plugins. The AI then decides when and how to use those capabilities based on the user's intent. The inversion of control is a fundamental shift in how you think about building these systems. The SDK handles all the mechanics for you. So, for example, prompt construction, functional serialization, retry logic, response passing. All of this is actually managed by the SDK, so you don't have to do it yourself. This means that your application code can stay focused on the business logic rather than the plumbing of AI integration. In terms of where it fits in your production architecture, semantic kernel sits between your application layer and your AI service layer. It does not replace your API gateway, it does not replace your authentication system as well. And just to make sure, it does not replace your observability stack as well. So those things you still need to do, but it does do a lot of different things. For example, what it depends does provide is that the integration with multiple AI providers. For example, Azure OpenAI, Hugging Face, NVIDIA, Google, and local models all work through a unified connector interface. Switching providers should require configuration changes, not code rewrites. Model context protocol is also now available and supported, which enables standardized connections to external tools and data sources. Memory connectors support Azure AI Search, Elasticsearch, Pinecone, and several others. So that's what it is, an orchestration SDK that bridges your application code and your AI services. Now let's look at the kernel object itself. So let's talk about the kernel object and how you register services with it. The kernel is essentially a dependency injection container, and but once that's actually specified for AI orchestration. It holds references to your AI services, your plugins, your memory stores, and your configuration. Every operation semantic kernel flows through the kernel. When you invoke a function or send a prompt, here's what happens. The kernel resolves which services to use based on your configuration. It constructs the appropriate request then. It handles the response from the model, and if the model requests function calls, the kernel manages that entire cycle as well. All of this happens through that central kernel object. One important design decision to understand here is that the kernel is stateless by design. Conversation history is not stored in the kernel. Memory is also not stored in the kernel. As the session which is not stored in the kernel as well. All of these are managed externally through chat history objects and memory connectors that you have to explicitly configure. This stateless design makes the kernel easier to scale and easier to reason about in distributed systems. Now let's talk about the service registration. You register AI services using builder methods. For Azure OpenAI, you would use add Azure OpenAI chat completion. For OpenAI directly, use add OpenAI chat completion. For Hugging Face, for example, you will use add Hugging Face text generation. and there are many more depending on your provider. Here's something useful. Multiple services can coexist with different service IDs. Text embedding services register separately from the chat completion services. So a single kernel can have one chat model for generation and a completely different embedding model for retrieval. This flexibility becomes important when you're optimizing for cost and performance across different tasks. If you have worked with ASP.NET Core Service Registration, the kernel builder should feel immediately familiar to you. It follows the same dependency injection conventions. For configuration best practices, you should be never hard-coding API keys or endpoints. You should be using environment variables, Azure Key Vault, or whatever secret manager your platform provides. The SDK supports configuration binding from configuration sources, so this should be pretty straightforward to implement. You should be setting explicit timeouts and retry policies at the registration time as well. The defaults are reasonable for development, but you will need tighter controls in production to prevent cascading failures when an AI service becomes slow or, for example, it might be unavailable. Finally, you should consider your kernel's lifetime pretty carefully. You should register your kernel as a singleton if it only holds services. You should register it as a scope if it holds per request state, let's say user specific plugins or memory contexts. Getting this wrong can cause subtle bugs that are difficult to track down, so please make sure you focus on this as well. Now that we understand what the kernel is and what it does, let's talk about what it orchestrates, which are plugins and functions. Let's talk about plugins and functions, which are the core building blocks that give you AI capabilities to your codebase. A plugin is a collection of related functions that you expose to the AI. Think of plugins as capability boundaries. A calendar plugin can handle scheduling, a search plugin would be responsible for retrieval, a database plugin will handle queries. Each plugin groups related to the function together, they combine it. There are several ways to define plugins. You can define them in code using the kernel function attribute. You can load them from the prompt template files as well. You can import them from the OpenAI specifications if you already have REST APIs documented. And now you can also consume them via MCP servers, which opens up integration with growing ecosystem of MCP compatible tools. Here's what's important to understand. The AI sees plugins and function names along with their descriptions. These descriptions are not optional documentation. They directly impact whether the model selects the correct function for a given task. Vague or missing descriptions can lead to incorrect function selection by the model. I've seen production systems break and have bugs because someone wrote a function description which is not exactly clear and specific. Instead of writing a specific description, what the function does and what it should be called, which leads to model not being able to call it. Now let's distinguish between the two types of functions. Semantic functions are prompt templates that the kernel sends to the language model. They transform input into natural language instructions and parse the model's response back into structured output. Native functions are regular code methods decorated with the kernel function attribute. They execute deterministically on your infrastructure. Database queries, API calls, calculations, file operations, these are all native functions. In production, most plugins combine both of these types. A semantic function interprets users' intent and extract parameters. A native function would execute the actual operation. Another semantic function might format the result for the user, and this combination will give you the flexibility of natural language understanding with the reliability of deterministic code execution. For function descriptions and parameters metadata, every function should have a description attribute that explains what it does in plain language. The model uses this description to decide whether to call the function or not. Parameters need their own descriptions explaining what values are expected out of them. You should include format hints, valid ranges, and examples when the parameter type alone could be ambiguous. Return type descriptions help the model understand what information it will receive, and which matters when the model actually chain together multiple function calls together. Now let's see how the AI actually invokes these functions through function choice behavior. Now let's talk about function choice behavior, which is how you control the interaction between language models and your functions. Function choice behavior is the current service agnostic API for controlling function calling. This is important as it replaces the older tool called behavior class, which is now being deprecated. If you're looking at older tutorials or documentation that references tool call behavior, you should migrate away to function choice behavior. The new API works across all supported AI connectors without connector specific code. There are three behaviors available. First is auto, which allows the model to choose zero or more functions from what you have provided. This is the most flexible option and what you will use most often. Second is required, which forces the model to choose at least one function. This is useful when you know a function call is necessary to complete the task. And third is none, which provides the function information to the model but prevents the invocation. This can be useful for scenarios where you want the model to describe what it would do without actually doing it. Now, let me explain how the function calling loop actually works. When you enable automatic function calling, the model can request function executions as part of its response. The kernel intercepts these requests, executes the functions, and feeds the results back to the model. This creates an iterative loop. User sends a message, model decides what information it needs, then model requests a function call. Then kernel executes that function and then result returns the results to the model. After that, model continues to reason. This loop can repeat multiple times until the model has enough information to respond to the user. These are configuration options that control this loop. Allow parallel calls lets this model request multiple functions simultaneously in a single response. Allow concurrent invocation lets the kernel execute those requests in parallel rather than sequentially. Both can improve performance when you have independent operations. For making function calling reliable in production, here are the key practices. You should be setting a maximum iteration limit to prevent runaway loops. If a model keeps calling functions without converging on an answer, it's either confused about the task or stuck in a reasoning dead end. Without a limit, this can consume significant resources. You should also be implementing function level guards that validate inputs before execution. The model might request a function call with invalid parameters. You should be catching this before you execute expensive operations or worse, irreversible operations like database writes. You should be also logging every function call with inputs and outputs. When production behavior differs from what you expected during development, these logs are how you diagnose whether the issue is model reasoning or function implementation. Without this observability, debugging AI systems would become extremely difficult. Now let's move on to memory and embeddings. Now let's talk about memory and embeddings, which is how our AI system retains and retrieves information. Semantic memory in semantic kernel stores text alongside its vector embedding. When you save a memory, the kernel generates an embedding using your configured embedding model and stores both the original text and the vector in your database. Retrieval works by embedding the query, searching for nearest neighbors in vector space, and returning the original text that corresponds to those vectors. This is the foundation of retrieval augmented generation patterns. The vector store abstraction provides two main classes. Vector store handles operations that span across all collections in your vector database. Vector store collection class handles all operations for working with individual collections. This abstraction is still evolving, so expect some refinements as the team gathers feedback from production usage. For choosing embedding models, Azure OpenAI offers text embedding A002 and the newer text embedding 3 family. The newer models offer better retrieval quality and configurable dimensions. Smaller dimensions mean lower user storage cost and faster search, while larger dimensions capture more semantic nuance. Embedding model choice affects the retrieval quality directly, so domain-specific embedding models typically outperform general-purpose models for specialized content. If you're building a legal document search system, an embedding model fine-tuned on legal text should outperform a general model. Test retrieval quality before committing to a model because switching later can mean re-embedding your entire corpus. The dimension trade-off is worth understanding. Higher dimension captures more semantic detail but increased storage requirements and search latency. For most applications, 1536 dimension represents a practical ceiling. Going beyond that rarely improves results enough to justify the additional cost. For vector store considerations, Azure AI Search provides hybrid search that combines vector similarity with keyword matching. This is valuable because semantic similarity alone sometimes misses relevant results due to specific terminology or exact matching requirements. Connector supports Azure AI Search, Elasticsearch, Pinecone, Chroma, and others. This abstraction should let you swap vector stores without modifying your retrieval logic, though in practice you may need to tune parameters for each store's characteristics. Local options like Chroma and SQLite with vector extensions work well for development and small datasets. However, you should be planning your migration path to production grade stores before you accumulate the data that becomes expensive to re embed. Now let's talk about how function calling has replaced planners and how the process framework handles complex workflows. Now let's talk about orchestration in semantic kernel, specifically how function calling has replaced planners and when you should use the process framework. This is an important update. The handlebars and stepwise planners have been deprecated and removed from semantic kernel. If you're following older tutorials or documentation that references these planners, you should know they are no longer are the recommended approach. Function calling is now the standard because it's more powerful and more reliable. Model language models excel at function calling natively. The model reasons about which functions to call and in what sequence based on the user's request. The kernel handles execution. This approach produces better results with less prompting overhead compared to the older planner approach, which required complex prompts to teach the model how to generate plans in custom formats. For multi-step tasks, enable automatic function calling and let the model iterate. It will call functions, reasons over the results, and call more functions until it has enough information to respond to the user. This behavior is often more robust than trying to predefine a plan. Now, there are scenarios where ad hoc function calling won't be enough. This is where the process framework comes in. The process framework handles structured, multi step business processes that require more control. You should think about, like, for example, account opening workflows, order fulfillment pipelines, or content publishing processes. These are cases where you have defined steps, compliance requirements, and audit trails. Processes are complex, composed of steps, and each step invokes user-defined kernel functions. An event-driven architecture manages transitions between these steps. Steps can be stateless or stateful with automatic checkpointing, which matters for long-running processes that might need to survive when the system restarts. The framework supports sequential execution, parallel processing, fan-in and fan-out configurations, and map-reduce patterns as well. For distributed scenarios, it integrates with Dapper and Orleans. Here's how to decide which approach to use. So, for example, you should use function calling for dynamic conversational interactions where the model should decide what to do based on user intent. This covers most chat based applications. You should use the process framework for repeatable business processes with defined steps, compliance requirements, and audit trails. In these cases, the workflow is predetermined and the AI assists within each step rather than determining the overall flow. The good news is that both approaches use the same kernel functions. Your investment in building plugins pays off regardless of which orchestration pattern you choose. Now let's look at the agent framework. Now let's talk about semantic kernel agent framework, which is now generally available. This is pretty significant news. The agent framework reached availability in late 2025. The milestone marks a commitment into stable, version APIs that minimize breaking changes and support production grade applications. If you were hesitant to adopt agents because of the preview status, that concern is now being addressed. Agents wrap the kernel with conversation management, instruction persistence, and thread based execution. An agent maintains its persona and capabilities across multiple interactions, which is different from stateless function calling, where each request is independent. The framework supports chat completion agent for standard LLM backed agents. It also integrates with Azure AI Foundry Agent Service for managed deployments where you want Microsoft to handle the infrastructure. OpenAI Assistance API integration is available here as well. For building effective agents, agent instructions define behavior, constraints, and persona. You should write instructions that specify what the agent should do, what it should refuse, and how it should communicate. You should be being more and more explicit. Vague instructions can lead to inconsistent behavior. And you should attach plugins to agent at the creation time. Each agent should have a focused plugin set aligned with the responsibilities. An agent that can do everything will often do nothing well because the model has too many options to choose from. Constrained agents with clear purposes tend to be more reliable. Here's a powerful pattern. Agents can use other agents as tools. A triage agent can delegate to specialized billing or refund agents. This composition enables sophisticated multi agent architectures where each agent has deep expertise in its domain. For multi agent orchestration, several patterns are now available. Sequential orchestration processes tasks through a pipeline where each agent builds on the previous agent's output. This is ideal for documentation review, data processing, or multi state reasoning where each step transforms the output of the previous step. Concurrent orchestration enables multiple agents to work on the same task in parallel, which results are aggregated at the end. This is useful for brainstorming, assemble reasoning, or gathering diverse perspectives on a problem. Handoff orchestration dynamically routes tasks to specialized agents based on the content. Group chat and magnetic patterns enable more complex collaborative interactions where agents can discuss and debate to reach better outcomes. The framework provides a unified interface across all these patterns. You define your agents, choose an orchestration pattern, start a runtime, and invoke. This consistency means you can experiment with different patterns without rewriting your agent logic. Now let's cover the production patterns that will make your deployment successful. Now let's talk about production patterns for semantic kernel, covering error handling, observability, and cost management. For error handling and resilience, you should wrap all kernel invocations in try-catch blocks that handle specific exception types. HTTP request exception, for example, indicates connectivity issues with your AI service. An exception like kernel exception indicates function execution failures. Exception like JSON exception indicates response parsing errors. Handling all these separately allows you to model to respond appropriately to each failure mode. You should also implement circuit breakers around your AI service calls. If the model endpoint failed repeatedly, you should stop sending requests and you should fail fast, which is a circuit breaker pattern. This will prevent timeout accumulation from cascading through your system and overburdening the already existing external service. Without circuit breakers, a slow or failing AI service can take down your entire application as threads will pile up waiting for responses. You should design fallback behaviors for when the AI layer is unavailable. Can users complete their task without AI assistance? Can you queue requests for later processing? Graceful deprecation keeps your application functional even when the AI components are struggling. For observability and debugging, semantic kernel supports iLogger for structured logging and activity for distributed tracing. Route these to your log aggregation and APM systems. OpenTelemetry integration is built in. Log prompts and completions, function calls, and latency metrics. This telemetry is essential for understanding why the system behaved unexpectedly in production. AI systems can be difficult to debug without this visibility because the same input can produce different outputs depending on the model state and context. You should be building dashboards that track token usage, latency, and function calling patterns. Usage spikes might indicate prompt inefficiency when you are sending more tokens than necessary. Latency spikes might indicate model capacity issues or inefficient function implementations. For cost management, token usage directly determines when you spend the most on which AI providers. For example, long prompts, verbose function descriptions, and extended conversation history can all multiply your costs. You should be measuring your tokens per operations and set budgets before you're surprised by a large bill. Also implement request level cost tracking so you can attribute spending to users, features, or tenants. This data informs pricing decisions if you're building a product and identifies optimization opportunities in your highest cost areas. You should cache responses where possible as well. If the same prompt with the same context produces deterministic results, you should cache their output. For another non-deterministic operations, consider caching intermediate results that are expensive to regenerate like embeddings or retrieval results. Now let's wrap up the guidance on when to use semantic kernel and when you might consider the alternatives. Let's talk about when semantic kernel is the right choice and when you might consider the alternatives. Semantic kernel is a good fit for enterprise applications that require structured orchestration of language models with conventional code. If you need plugins, function calling, memory, and agents to work together as a cohesive system, semantic kernel provides that integration out of the box. It's particularly strong for teams already invested in the Microsoft C# and Azure ecosystem. However, it also supports other ecosystems just as normally. Native integration with Azure OpenAI, Azure AI Search, Azure AI Foundry, and other Azure services reduce the friction. If you are deploying to Azure, the operational work here is pretty straightforward. For applications requiring strong typing and compliance, compile time safety, the C# SDK offers the most mature type system for AI orchestration. If reliability and maintainability matters more than the rapid iteration speed, this helps catch errors at compile time rather than the runtime. So now when you should consider the alternatives. If your use case is simple chat completion without function calling or memory, raw SDK calls to OpenAI or Azure OpenAI are much simpler. There is less abstraction overhead, fewer concepts to understand, and less code to maintain. Not every application needs the full orchestration capabilities. If you need capabilities that have not yet reached general availability, evaluate whether your timeline aligns with semantic kernel roadmap. Some features remain in preview, and building production system on preview APIs definitely always carry risk. If your team works primarily in languages other than C Sharp, consider this carefully as well. While Python and Java SDKs do exist and have reached version 1.0, the C Sharp implementation has the most comprehensive feature set for semantic kernel. You may find capabilities available in C Sharp that are yet not ported to other languages and might take some time. For the decision framework, evaluate build versus buy trade offs honestly. Semantic kernel provides significant infrastructure but for free. But you also take on Microsoft abstractions and they upgrade cadence. Make sure the abstractions fit your mental model before committing. Start with the simplest implementation that solves your problem. If raw API calls work, you should use them. If you find yourself building orchestration logic, memory management, and function calling infrastructure, then add semantic kernel. Do not adopt complexity before you actually have the complexity to address. Finally, you should remember that production AI systems require more than an SDK. Authentication, rate limiting, content filtering, cost controls, and observability are your responsibility as well. Semantic kernel handles AI orchestration. Everything else, like what I just mentioned, is still the work you need to do. So that was a complete deep dive of semantic kernel. Now, ideally, you should be able to understand and be aware of kernel abstraction, plugins and functions, function choice behavior, memory and embeddings, and the process framework, the different concepts for semantic kernel. I hope you found it valuable. If you have any questions, please feel free to let me know. Thank you and have a good day. Bye.